You may want to pause the video and reread the problem before listening on. We're given several pieces of information, and we're going to kind of come down and zoom in on the circuit here and analyze those pieces of information. So, for instance, we were told that through point A, an amount of charge equal to 12 microcoulombs has passed. Also, through point B, 8 microcoulombs of charge has passed. Now, if you notice, there is a junction in the circuit right here. And when 12 microcoulombs of charge enters that junction, what happens is the charge splits. And we know that 8 microcoulombs are going to travel off in this direction to the right. So you have to ask yourself, well, if 12 microcoulombs of charge are coming into the junction and 8 microcoulombs are coming out, how much charge must also be coming out of the junction but flowing in the downward direction? And the answer to that is 4 microcoulombs, because the amount of charge that's coming into the junction, which is 12 microcoulombs, must equal the amount of charge that's coming out of the junction, which would be the 8 microcoulombs plus the 4 microcoulombs. So we know that 4 microcoulombs of charge is traveling down this vertical section of the circuit. So that's how much charge is going to build up on C3. And over here on C4, if we follow this arrow, we can see that 8 microcoulombs of charge is going to develop on the plates of C4. Now, we know a relationship that governs the charge, capacitance, and potential difference across the plates of a capacitor. So, if we wished, we could analyze C4. And we could say that the charge on the plates of C4 is going to equal the capacitance of C4 times the potential difference across the plates of C4. Now, we look at C4, we can see that the charge, again, was 8 microcoulombs, and the capacitance is 4 microfarads, and that's multiplied by the potential difference across the plates of capacitor 4. Now, if you divide both sides by 4, you can see that 2 volts would be the potential difference across the plates of C4. So we can go over there and we can label it. And what's interesting is that C4 and C3 are in parallel with one another. You've probably learned in this chapter that when two capacitors are in parallel, then the potential difference across their plates is the same. So if the potential difference across C4's plates is 2 volts, then the potential difference across C3's plates is also 2 volts. So we can label 2 volts for that capacitor as well. But now that's interesting, because if we use this same equation but apply it to the C3 capacitor, we could say that Q3 is equal to C3 times V3. We know the charge on the plates of C3, that was the 4 microcoulombs that we analyzed earlier. And we are looking for C3, so we don't know that, but we now know that V3 is the 2 volts. So dividing both sides of this equation by 2 yields an answer of 2 microfarads as being the capacitance value of C3. That was what was being asked for in part B of the question. We wanted the value of C3. So we now know that that is equal to 2 microfarads. The only thing we need to analyze next is the capacitance on C1. So that's what we're going to do now. And to do that, we go back to point A, through which 12 microcoulombs of charge has flowed. Now, you might notice that point A and C2 and C1 are all arranged in a series arrangement, which means that the amount of charge flowing through those 3 elements is the same. So that means that C2's plates is going to have a charge of 12 microcoulombs, and C1's plates are also going to have a charge of 12 microcoulombs. Another useful piece of information for us to find is the potential difference across the plates of C2. Now again, we can do that by looking at the equation that governs these quantities. We know that Q2 would equal C2 times V2. We know the charge across C2's plates, that are stored on C2's plates, I should say. That was the 12 microcoulombs. We know that C2 has a value of 3 microfarads. We can solve for V2. If we do so, we divide both sides by 3, and we get 4 volts is the potential difference across the plates of C2. So let's label that. And now what we're going to do is conduct an analysis to figure out what V1 would be. So right now we don't know the potential difference across the plates of C1, but if we could figure that out, if we knew the potential difference, then we could easily calculate the value of C1. So this is going to become our goal, and to accomplish that goal, we're going to clean up the picture just a little bit. Our focus right now is on the potential changes, the potential differences across the terminals of the battery or across the plates of capacitors. Now, there's a particular rule that you're probably going to learn later on in a future chapter. It's known as a loop rule. We're going to give you a preview of the loop rule by kind of traversing a loop and kind of moving our way through the circuit. Now, we're going to actually follow this loop right here. And as we go through this loop, we're going to be keeping track of potential changes. So what we'll do is we'll start at this location in the loop. We're going to be in proximity here to that smaller plate of the battery. Now that smaller plate of the battery is going to have a potential of 0 volts, and then the larger plate is going to be 9 volts. And we know that because the question said the battery provides a potential difference of 9 volts. So what we're going to do is we're going to start at little point X there, and we're going to go around the yellow loop through the circuit. And as we do so, we're going to keep track of these potential changes. So here we go. We're starting at X. We're going from 0 volts up to 9 volts. So that's an increase of 9 volts. And then we kind of go through the circuit through the yellow pathway here. We encounter C1. Now there's going to be a potential drop there, but we don't know what it is. We've labeled that X volts. And therefore, because it's a potential drop, we're going to subtract the X volts. We continue our way through the circuit. We encounter this capacitor next. We know the potential difference or the potential drop there is 4 volts, so we're going to subtract 4 volts. And then we continue through the loop. We make a turn here, and then we go through C3. We know the potential drop there is 2 volts, so we're going to subtract 2 volts there. And by the time we continue our path and return to where we started, we return to X and complete our loop. Now, in the loop rule, you're going to set all of these potential changes equal to 0 volts. The loop rule says that when you follow your way through a loop, through a circuit, the sum of the potential changes is 0. It would be analogous to getting on a roller coaster where your initial gravitational potential energy would be 0. You go up a hill, you go down the hill, and a bunch of loopy-loops and so on. But by the time you return to where you started, your net change in gravitational potential energy is 0 because you've returned to the same height. It's kind of the same idea here. The overall change in electrical potential is 0 when you work your way through a loop. Now this is a nice equation that we can solve for X. We might want to drop the units here just to show you what we're solving for. Kind of would look like this. And if you combine like terms on the left side, you're going to have, let's see, 9 minus 4 is 5, 5 minus 2 is 3. So we have 3 minus X is equal to 0. We solve for X, we get X is equal to 3. So remember what that X was. That was the potential drop across C1. It's now known to be 3 volts. So we can come back here and we can enter that value into our little picture here. And now that we have that value, we can actually calculate C1 because we know that Q1 is going to equal C1 times V1. We know the charge stored on the plates of C1, it's 12 microcoulombs. We don't know the capacitance value, but we now know that the potential difference across the plates there was the 3 volts. So we'll plug that in for V1. We divide both sides by 3, and we can see that 4 microfarads is the capacitance C1. That was the correct answer to part A of the question.